Okay, so there we go. Welcome to the second lecture in cryptography. The main topic for today is going to be a similar one as for the next two lectures, namely we're going to talk about symmetric primitives. So these are the building blocks that are inside all the symmetric um, cryptographic schemes, like encryption schemes or hash functions and so on. And what's the plan for today? First, I want to talk a little bit about the general role of primitives in the crypto stack, so to say. So what is their place in the stacked model of cryptography? What are the things they do offer? What are the things they don't offer? And then for specific primitives, we're going to look at what we call their black box properties, which is if we consider the building blocks just like a black box where we only know its interface but not the internals, what can we say about its security? And after these black box properties, we want to have a look inside the cryptographic schemes. So we want to see how they are constructed, what different strategies there are. So we will briefly revisit one primitive that you may already know from information security, namely the AES, but we will also have a look at a few other ones. And there is also one important topic that you probably haven't heard much about yet, but that's very relevant when building other primitives that are not block ciphers, namely so-called generic compositions, which means you take a primitive and then you make a transformation to get a different type of primitive. And finally, at the end, we will have a look over some of the standardized ciphers that are currently in use. So let's first talk about the role of primitives. As before, if there are any questions at some point, please just interrupt me by speaking up. I'm also monitoring the chat on Teams. I'm not monitoring the chat on YouTube, unfortunately, so I can't look everywhere. So let's talk about the role of primitives and what role they serve in the crypto stack. So this is a simplified picture of the crypto stack. So whenever you do something like you kick on your browser and connect to an HTTPS website or so, then a whole stack of things happen inside. The topmost layer, or one of the topmost layers in the stack, is what we call protocols. So an example for this is TLS, which is the protocol that is responsible for the secure S in HTTPS. So what a protocol is it's an instruction about what some defined parties should say to each other, which messages they should send to each other in order to achieve something like building up, for example, a trusted connection with each other and then being able to send data. So it's like the whole framework, and it really defines the messages being sent back and forth for a particular application. What's going on inside the protocols is that we're usually running some so-called cryptographic schemes. So what's the difference between protocols and schemes? An example for a scheme is, for example, the encryption scheme AES-GCM or the hash function SHA-2 or so. So schemes also have a specific purpose, but a scheme is usually just one algorithm. It's a function where you put some values in, you get some values out, that's it. Whereas the protocol tells you how to use the scheme and which messages to send in, and which schemes to call in order to produce the messages. Finally, inside the schemes, we have yet another layer that we want to talk about today, and that's the layer of primitives. An example for a primitive is the block cipher AES. Another example is the compression function inside SHA-2, for example. So these primitives inside, what do they do? Now, these are fixed size boxes, so to say. So algorithms that process a fixed size input and output. And these are usually used in a loop inside the schemes so that the scheme can process data of arbitrary length. So for example, you should be able to hash a message or a file that's 1 kilobyte long or 5 gigabytes long or just 1 byte. All of this should work. And the primitive is what's going on inside the for loop that goes over the length of the message. So that's the thing you apply to each block, for example, of the message that you produce. And what primitives typically do is either they translate the input blocks one by one, or they might accumulate some information. So it starts with some value and then it absorbs some information from the first block plus some from the second block and so on. So the difference between schemes and primitives is that a primitive is something that already has something like a security level. So you can say this thing is 128-bit secure, but it doesn't yet give the functionality that we expect. So it only processes a fixed size input. And to be able to apply it to any useful data, we need to build the scheme on top, which also has a security level like 128 bits, but is able to process the long thing. So the typical tasks of a primitive are, as I said, either to translate data blocks or to accumulate data. And the idea is that today we want to talk about what's inside the boxes, so the primitives, and we will start talking about the modes sometime later. I think it's in the last week of October that we start talking about that. So if you already heard information security, you have already heard these two terms. So in information security, we mostly talked about the modes, and we only had a tiny bit about the primitives. And here in cryptography, we will talk 3 full lectures about primitives. So today, I want to give you some basic information and the basic construction mechanisms that we know for blockwise primitives. Next week, we will talk about some more lightweight primitives and also some alternative primitives like stream ciphers, which don't process data in blocks, but by different means. And the week after that, we take a closer look at cryptanalysis of primitives. So in particular, we will have a look at how differential cryptanalysis works, as well as some other cryptanalysis mechanisms that are relevant for primitives. So that's the plan. Today, some of the most widely used primitives. Now, which primitives are there actually? The most famous one and the one most people know is the so-called block cipher. So this is like an encryption scheme, but in miniature, meaning it can only encrypt fixed size data blocks. For example, 128-bit data blocks. So it's a bijective function that translates the input to some output. And the way in which it exactly translates is configured by the key. So the key input is usually indicated with this little edge on the left-hand side of the box. We also have a couple of other primitives that are a bit less well-known, but nevertheless very useful. One of them is the so-called compression function. So what this does is also it takes a fixed size input, which actually consists of 2 parts, and compresses it to a fixed size output, where the output is the same size like one of the 2 input blocks. This is sort of the chaining value that we are maintaining. And what it adds to the chaining value is it absorbs in a block of message. So with this, you can update a current state based on some message and you get a new state and you continue processing from there. A permutation is a bit similar in that it updates a large state and continues from there, but it doesn't actually have a separate input like for a text, for example. It just processes a state and gives you a new state, and that's it. If you want to add in any messages, you must do that yourself. And finally, there is a primitive that, like permutations, has become quite a bit more popular recently. So in very old books about symmetric crypto, you find almost exclusively block ciphers and maybe a bit about how to turn a block cipher into a compression function. Whereas many of the schemes that have been proposed more recently and that have very attractive properties actually use one of these 2 schemes, primitives. So either permutation or a tweakable block cipher. So what is a tweakable block cipher? It's like a block cipher, but it has an additional input that also influences the choice of the function that translates the plain text to the ciphertext. So not only the key, but also the tweak modifies this process. And the difference between the tweak and the key is that usually somebody who uses a block cipher uses the same key for a long time, but it's secret. And the tweak is the exact opposite. So you usually use a fresh tweak every time, but it's public. And what's the point of this tweak? So it actually adds something that we will see in a few weeks is missing in the standard block cipher. So in the standard block cipher, it looks like a perfect basis for an encryption scheme because it translates stuff and encrypts. But what's really missing here is any way to input some sort of context. Like, for example, in which position in the message is this cipher? Or part of which message is this plain text block here? So the same plain text block would always be translated the same in case of a simple block cipher. And you have to do some tricks in order to get actually rid of this and to make sure that the same plain text does not always lead to the same ciphertext. And one way to do this, to take this context into account, is this tweak here. So this is a sort of modifier that tries to bring the context into the block cipher translation mechanism. So now I explained which types of primitives there are, but I would actually be interested in which specific primitives, besides, for example, the AES, you already know, which is why I've opened a little poll here, which I can bring on screen right now. So you should now be seeing a relatively blank slide with a link on top. So it's menti.com. You need to enter some code there. And once you do, you will actually be able to enter some keywords. So let's see if any of you already know some primitives. Okay, there we already have one. RSA, an asymmetric primitive. That's right. That's another symmetric primitive. ECC, elliptic curves. We will hear more about that later in the lecture. Triple des, yes, that's another block cipher. SHA, yeah, while SHA is actually not itself a primitive, of course, it does have a primitive inside, namely the SHA compression function. And SHA-256 is a particular variant of that. And it's like an advanced version of MD5, which I see here. Somebody is saying Diffie-Hellman. Yes, Diffie-Hellman is a sort of primitive. It's also at the same time the name of a protocol. So this is a point where the distinction between the primitive and the scheme and the protocol is a bit vague, a lot less clear than for some of the other ones. Oh, somebody knows ISAP. Well, ISAP is an encryption mechanism, but it's actually not a primitive. It can have different primitives inside. Maybe one of you knows which ones. Yes, the ASCON permutation is one of the primitives that you can use inside ISAP. Maybe somebody knows the other one that we can use. Let's see if there are a few more suggestions, or if you're already powered out. Okay, it looks like not so much more is forthcoming, but that's already a pretty nice collection. You may want to keep this tab open because we will have some more suggestions later on. So there was some addition or reorganization, but I don't see exactly what changed. Oh, Caesar, yes, the Caesar cipher, so the very classic Caesar cipher that we saw last week, is of course also sort of primitive, if not a particularly secure one. Somebody added something more on elliptic curves. That's also nice. Okay, so I'll keep this tab open and maybe we will have a look later if somebody still managed to add something. Maybe one of you can also copy the code quickly to the chat. I can unfortunately, well, I can actually do that as well, even though my Teams is not very responsive, but I guess we will manage. Oh yeah, the code is already there. And now the link is as well. So in case you decide to join up later, you can of course do so. And in the meantime, I go back to my slides if I find them again. Okay. So let's now have a look at the black box properties that the schemes we saw so far have. So what is the interface that the different primitives have, and what influence does it have on the security? Oops. So let's first talk a bit about block ciphers, because we can talk about the other things once we have talked about block ciphers. So the ideal block cipher model that we would like to have, or the ideal interface, is, so we have these n-bit input blocks, we said, which is the message that is to be translated, which means we have 2 to the n possible inputs in total, so as many different message blocks that we can encrypt. This now looks a bit like what we already saw last week. Last week we already said that if I have this many message blocks, then there are a total of 2 to the n factorial possible translation rules that translate these plain texts to ciphertext. This is because if there are 2 to the n possible plain texts, then we also have 2 to the n possible ciphertexts and ciphertext values. And by creating a lookup table where on top we have the plain text and on the bottom we enter all the possible ciphertext values, any reordering of these ciphertext values, of which there are this number factorial many possibilities, each of these reorderings gives a valid permutation that we can use as a block cipher, so a translation mechanism from plain text to ciphertext. And this number actually grows very, very fast. So if we only consider 6-bit blocks, which is less than 1 byte, so here you already see 3 bytes, so this is like less than 1/3 of what you see here. For such small blocks, there are already more possible translation rules than there are keys for AES 256. So this means it's very easy to create a very large key space here, but what we want for a block cipher is that our keys select some random translation rules from the total set of 2 to the n factorial options. So what we would ideally have is that, for example, if we have a 256-bit key, that each possible key value selects randomly one of these lookup tables in some way. So an ideal block cipher with a k-bit key corresponds to a random selection of 2 to the k from these 2 to the n factorial instances. So this is the idealized version. This is, of course, not a practical version. So actually implementing this is, of course, not so easy. We need some way to first select these lookup tables and then also to describe them precisely, so that if we know one particular key, we can easily translate all the blocks, ideally without storing the complete lookup table. So this is what we would like to have. So to name again the interfaces that we have, so we have a k-bit key, an n-bit message, and we generate an n-bit ciphertext. So far we've only talked about the left-hand side here, so the encryption mechanism. But of course, in addition to the encryption, we also need a decryption mechanism, which in particular means that this function we have here must be bijective or invertible, which means, if we look back to the previous slide, that every plain text is not only mapped to a unique ciphertext, but also every ciphertext value is mapped to a unique plain text. So there must be no duplicates here. Now let's have a look at what sizes could be suitable for these k and n. Let's first look at n, the size of the message. In the previous example, n was pretty small, because then there are already many possible keys. However, if we have a very small n, then if we process more parts of our data with this function, then we will often find collisions. So we will often accidentally run into the same message again, which will then lead to the same ciphertext again. And if this happens too often, then it's too easy for an attacker to, for example, see patterns. or to reconstruct the lookup table from messages to ciphertext without actually knowing the key. So that's a downside if n is too small. If n is too large, of course, the implementation is a bit more complex because we need to store larger blocks at a time, and also the update function is going to be a bit more complicated. There is one trick that we already saw which can help to alleviate the problems of small n without all the cost of a large n, and that is to add an additional tweak input, which is different for each message block we process, so we don't have this collision problem. Now let's have a look at the key. There are 2 to the k possible keys here, so 2 to the k mappings or lookup tables that we can generate. If this k is very small, then an attacker could simply try all the possible values of this key, so do a brute force attack. Whereas if it's too large, we again have a somewhat higher cost. So overall, in all of these cases, it's usually the case that if the security value becomes too small, you very quickly run into security problems. Whereas if you make them larger, you don't really, after a while, you don't gain too much security anymore, but also you don't gain too much cost overall, which is why some people don't really care if they use a 128-bit key or a 256-bit key. It doesn't make that much of a difference for evaluating in most cases. Let's have a look at compression functions next. So here we also said they have a fixed input and output size, but they have different roles. So we have this state that we're updating, which is t bits large, and we have a message, which is again m bits large. And this is now one fixed mapping. So we are not really defining a family of mappings like before, but just one fixed mapping with 2 to the t plus m possible inputs and 2 to the t possible outputs. So in the previous case, for the block cipher, we usually had the case that in an application, the key usually stays the same and only the data changes. But for compression functions, usually all of this changes all the time. And t is again a very important indicator for the security level. So if t is small, then it becomes a lot more likely that we accidentally have the same output here twice for 2 different inputs. And if we have that, we have a so-called collision, which can usually be exploited. Whereas if t is very large, we again have a somewhat higher processing cost. So I've now said a lot about small and large, but I haven't been really specific. So how do we really quantify now the security of a cipher? Now, one way to do this is the so-called T epsilon security curves. So what does that mean? We say that a cipher is T epsilon secure if any attacker who invests up to T time, for example, tries T encryptions or so, has a success probability of at most epsilon. So, of course, there's not just one possible T epsilon value for a cipher. So, for example, for a cipher with a 128-bit key, if the attacker invests 2 to the 128 time, then the success probability is somewhere close to 1. Whereas only if they only invest, for example, 2 to the 64 time, the success probability of any attack is negligibly small. So what this is here is not some fixed parameters, but it actually describes a curve. For which time t do we get which success probability epsilon? And there are now 2 things that define these security curves or that limit them. And the first thing is what we've already discussed a bit, so-called generic attacks. So a generic attack is an attack that works for any cipher with the same interface. So for example, for any block cipher with a 128-bit key, there is a brute force attack, namely guessing the key, which has 2 to the 128-bit cost and secure success probability approximately 1. There is however, also a different type, namely so-called dedicated attacks. Dedicated means we're not just looking at the interface, but we're looking at the actual internals of the cipher and exploiting these internals. So for example, we look at the round function and see if there are any weaknesses in there. And so there are usually two prerequisites for us to call a cipher secure. So the first prerequisite is that it's actually secure in the sense that the security indicated by its parameters is good enough for our application. So for example, the key is at least 128 bits large. So this is the generic security. And then there is what academic cryptographers are very interested in, namely whether there are any dedicated attacks which are better than the best generic attack. So in other words, are there any weaknesses in the cipher that allow an adversary to recover the key or do some other attack faster than the best generic attack? So what we want to make sure is that the internals are strong enough that any attack that exploits the internals is not cheaper than the cheapest generic attack. And what a cipher designer is usually expected to do is when they come up with a new cipher, they're supposed to first explain that the generic security is good, which is usually very easy. And then they're supposed to write down in a so-called security claim what this generic security is, or what they claim it to be. And then they give a rationale, so an explanation and arguments why they think that dedicated attacks are no better than generic attacks for this cipher. So that's the big goal. And you will often hear people say that, for example, a particular algorithm is broken. What they usually mean by that is that somebody has found a dedicated attack which is at least a tiny bit faster than the generic attack. So as an example, if you have a 128-bit block cipher and you find a dedicated attack which would cost 2 to the 120, so by a factor of 2 to the 8 less than the best generic attack, and which still has a good success probability, then we would say that the cipher is academically broken because it does not satisfy the promises it made in the security claim. So being academically broken does not mean that it's practically broken, because 2 to the 120 is still completely unfeasible. However, it means that there is a weakness there which wasn't anticipated. And over time, these attacks usually don't get weaker, they get stronger. So once there is a weakness, it is to be expected that the security level is going to erode further. And this is one of the reasons why an academic attack, even if it's not immediately practical, should usually be used as a critical warning sign to abolish the cipher. So for example, for the hash function SHA-1, such academic attacks have been known since 2005, but it took 12 years until somebody actually managed to, at least to public knowledge, until somebody actually managed to pull it off and find a collision. But this was at the time no longer unexpected, at least for cryptographic researchers, because the academic attacks, so the dedicated attacks faster than generic attacks, had already been published for years. Okay, so let's have a look at what defines these curves, because so far we've only always talked about the end point of the curve. Like if you try all the keys, then you're pretty sure to find the correct one. But what if I don't try all the keys, but just some of them? And to explain these curves for different primitives, there are a total of 4 combinatoric experiments or values that are helpful for our understanding. So in all of these, we're talking about randomly drawing some balls from a bowl. So we have a bowl which has a number of numbered balls inside, which all have different numbers. And we're grabbing a handful of them and looking at the result. So in total, there are 2 to the power of n balls in there, and we are drawing t of them. And the first 2 questions we can ask is, assume that one of the balls in there is a golden ball. Now, what is the probability that in the t balls that we pick out, there is the golden ball among them, if we are drawing without replacement? in German ohne zurücklegen. So what that means is we simply grab T balls at once, look at them, and that's it. It's not like we're picking a ball, looking at it, throwing it back in, picking another one, which might be the same or a different one. So throwing back in and taking the next one is called with replacement, whereas grabbing them all at once and just looking at the set we have is called without replacement. So if we look at without replacement, we have T balls in our hands. They're all different. And the question is, what is the likelihood that there is a golden one among them? So these probabilities usually always have the format in German günstige durch mögliche. So the good results we're interested in divided by all possible results. And all possible results for the balls in this case there are 2 to the n possible results. And so this is the position of the golden ball, and there are T good results. What is a good result? It's if the position of the ball is in one of the first T ones that we drew. So if we index them all that we have drawn and all that are still in there, if the ball is in the first T, so T good places, then we are successful. So this is the case without replacement. What if we do it with replacement? So we take a ball, look at it, throw it back in, take the next one, and so on. Now the probability is a bit different. So to compute the probability, what is the likelihood that we have the golden ball? It's actually a bit easier to say what is the probability that we don't get the golden ball, and then just subtract it from 1. So 1 is all cases minus the cases we don't want, which are the cases where we don't draw any ball. And in order to not draw any ball, we need to not draw a ball T times in a row. So some probability needs to hold T times in a row, so something to the power T. And now let's look at the probability that one of the balls we pick is not the golden ball. Well, the probability that it is the golden one is 1 divided by 2 to the n. And the probability that our ball is not the golden one is 1 minus that. So this is the overall expression that we get. Okay, so much for searching for golden balls. Let's now have a look at a different experiment. Namely, I'm interested in the probability that I draw the same ball twice. And again, we have 2 scenarios. We can either draw them without replacement or with replacement. The first probability is very easy to answer. So if I draw the balls without replacement, meaning I take only different ones, then the probability that I take the same ball twice is 0. It can't happen. However, if I draw with replacement, meaning I take a ball, throw it back in, take the next, and so on, and I want to see whether any 2 balls I drew are the same. For example, I drew the ball number 3 twice. Now, what is the probability for this one? We can do it a bit similar as we did the computation up there. We can again say, what is the probability that I don't draw the same ball twice, meaning I draw all different balls. So in that case, let's look at each ball in turn, and let's see what's the likelihood that this ball is different from all the ones I've already drawn. So for the first ball, the probability that I've already drawn it is 0. It's definitely a new one. I've definitely never seen it because it's a first ball. So the probability is 1, that it's not a collision. Let's look at the next ball. Now there is 1 out of the 2 to the n candidates. If I hit that one again, it would be a collision. So 1 over 2 to the n. But in all other cases, it's not a collision. And I can continue this way for each ball number I. So for the ith ball, there are I minus 1 balls I have already drawn. They would all be a collision. So 1 minus that means it's not a collision. And if I compute the product, so this is the product symbol, if I compute the product of all these successive probabilities of not having a collision and subtract it from 1, then I get the overall probability that I have a collision. Now, this term is a bit unwieldy, so we can't use it immediately. But we can do some trickery and rephrasing to see that what we have here is approximately something like t choose 2 times 1 divided by 2 to the n. So t choose 2 is in German called n über k, and it's the number of possibilities how I can draw k, in this case 2, out of t candidates. And what this means intuitively is I have drawn t balls, and any selection of 2 of these t balls is a possible pair that could be a collision. So I have t choose 2 possible pairs, and each of them is a collision with probability 1 divided by 2 to the n. So if I multiply this out, what I get is again approximately something like t squared divided by 2 and divided by 2 to the n. So the important thing here is that t is squared before being divided by 2 to the n. And this is different from the case up here. So what we're seeing here is another explanation of the birthday paradox that you might already have heard about. But what these formulas give us is these curves here that correspond to the security curves, to the t epsilon curves of different types of cryptographic attacks. So let's first look at the red curve maybe. So the red curve is the success probability of finding a preimage of some permutation. This would, for example, be that I correctly guess the plaintext that corresponds to a given ciphertext. So there are 2 to the n possible options, and I can just try them one by one. One of them must be correct. So as soon as I've tried all of them, the success probability is 1. If I've only tried half of them, so 2 to the n minus 1, note that this here is a logarithmic scale. If I've tried half of them, then the success probability is, well, 1/2, and so on. So if I've tried a quarter, it's 1/4, and so on and so on. So this is the red curve here. It's a bit different if I'm trying to find a preimage of a non-invertible function, so like a compression function f, because here I cannot simply try all possible messages until I hit the one that gives me the correct output. What I need to do instead is I can try many of them. However, even after I've tried 2 to the t possible messages for a t-bit output, I am not guaranteed to actually have found something, because I may have found some other tags twice, but not found the tag that I'm looking for. This is because this is drawn with replacement, meaning 2 different inputs can actually give the same output. This is like drawing balls with replacement, whereas this is without replacement. So the success probability for this is overall a bit lower, and it takes a very long time before this actually reaches 1. So it reaches something like 90% or so quickly, but then it takes a long time before it reaches, if it ever reaches 1. And there's another very interesting curve here. You will notice that whereas these become something reasonable around 2 to the n, this green curve here already rises at 2 to the n divided by 2. And this is because this is the curve for collision finding. So here is where the birthday paradox kicks in, that I already find a collision among samples, which corresponds to finding the same ball twice with replacement in the previous page. This already becomes successful around 2 to the n divided by 2, because there I have already approximately 2 to the n candidate pairs among all my samples, and if one of them is correct, then I have 1. So in particular, we see that if I take around 2 to the n divided by 2, I have a success probability of something like 40% or so. And if I take a bit less, for example, half as much, I have something like 10% or so. Here the curves become negligible. If I would have drawn this axis here as a logarithmic axis instead of a linear axis, then these would actually have been straight lines here. So if you're interested in getting a deeper understanding of this picture here, one thing that makes sense to do as an exercise for yourself is try to draw this picture here on a doubly logarithmic scale. So here a logarithm and here a logarithm. Okay, so these are some of the curves that directly also correspond to some of the challenges like key recovery or finding pre-images or finding collisions in a hash function. So we've now talked a lot about powers of 2, but just as a reminder, how hard are these different powers of 2 actually? So you will see that I've drawn this for 3 different units here. First, time, second, memory, and third, data queries. Where the difference between these two is, by memory, I mean storing this much in my RAM, and by data meaning I get this many samples that were encrypted with the real key. For example, I'm collecting known plaintext ciphertext pairs or something like that. In the case of time, something like 2 to the 32 or so is completely trivial. So if this is a fast cipher and it's a fast CPU, it's something like 1 second or so. If one of the two is a bit slower, then it can also be a minute or whatever. 2 to the 48 is still pretty feasible, even as a private person. You will just have to wait a bit and or invest in some more cores. 2 to the 64 is something that you yourself might not find practical, but there are definitely people here who can already do that. If we go towards 2 to the 80, it's becoming a bit narrower. So I don't think anyone would actually currently want to invest this much money into attacking someone. But I wouldn't rely that this remains true for 20 years or so. And finally, once we're in the area of 2 to the 128 or more, this is pretty infeasible, at least on a classical computer. For memory, you see that I've turned it red a bit earlier, because storing a particular amount of data is usually more expensive than generating this amount of data. So in particular, storing something like 2 to the 32 cipher states already corresponds to several gigabytes. So this might be feasible on your machine, but depending on how large the cipher states are and what else you do with your RAM, it might already be difficult. And it becomes infeasible pretty quickly, according to my estimates. And for data, it's even a bit more difficult because for collecting data, you don't rely on your own complexity that you invest in your own machine, but you rely on what somebody else does for you. And this somebody else is usually not somebody who's driving their CPU up to 100% and just serving you the data, but they usually just occasionally encrypt something or so. So collecting these is, again, usually more difficult. So what requirements do we have for ciphers to reach these particular security levels, where security level corresponds to the exponent of the attack complexity? So for 128-bit security, in case of a block cipher, we typically want, for example, a key with 128 bits, such that brute force key guessing takes as long. For the block size, actually, we can consider different block sizes, and they may all work. However, if we have smaller block sizes, then this means that I have a higher danger of collision. So some other attack that is not key guessing may become the critical factor. And for hash functions, due to the birthday paradox, it means that we need at least twice the security level as a hash output size. Okay. So it's time to do something interactive again and wake up a bit. So let's first go back to our cipher. I see there haven't been too many updates since I last opened it, but let's go on to the next slide. So this is a ranking question. What you're asked to do is you're asked to rank these in order of their security. So the first one should be the most secure, and the last one should be the least secure. And you can enter your guesses, and this will display a sort of aggregate view of all the guesses. And you will be asked to first select the strongest cipher, then the next strongest, and so on. So let's see what you come up with. Okay, there is some dispute as to whether the big compression function is more or less secure. Let's see how it develops. Okay, so there is some disagreement apparently about the relative position of these two and of these two. They swap occasionally. But you seem to agree that this one here is the strongest. And indeed it is. It should offer approximately 256-bit security with respect to key recovery. But of course, the smaller block size might make it possible for some other attacks to happen. Here, I would disagree with the current state. So what is the security of a 224-bit compression function? A compression function is a building block for a hash function, and the output of it is also the same size usually as the hash output. So if this is small, we always have the danger of collisions in there. And what is the cost? How many samples do I need to collect to get a collision here? Well, approximately 2 to the t divided by half, which is 2 to the 112. So this is more like 112-bit security. Whereas this here is definitely 128-bit security. So these two should be swapped here. And a similar argument also holds for these two here. So this compression function here has 64-bit security, whereas this one has 128-bit against key recovery, but approximately 64 against other attacks that are, however, more costly because they require queries. So these two should also be swapped here. Between this compression function and this block cipher, I would say it's a tie. So they should end up on the last two spots. Okay, thanks for your inputs. Let's head back to the slides. And let's have a look at how to construct primitives. Because the challenge that they essentially try to solve is they try to build security from scratch. So we said that this is more or less the bottommost layer. It's definitely the bottommost layer that has a security claim. So if you look inside the primitives, anything that goes on inside there has no security level by itself. It's just a sort of meaningless circuitry, so meaningless from a security point of view. Whereas the primitive is the first thing that promises a security level. And everything above it tries to prove their security based on the security of the primitive. So the primitive is really the foundation of this whole building. And if it collapses, everything above collapses. And it has, of course, a difficult job because it's supposed to build security from scratch. So what is the thing that we are trying to achieve here? So we're trying to get away from this ideal block cipher model where we said it's just a randomly drawn mapping of plain text to ciphertexts, which is complex to specify, complex to transfer, and so on. And we want to just have an unknown key on which the security rests, whereas the rest should be some known and simply describable function. So what we want is we have some function here that describes us, based on the key, which plaintext goes to which ciphertext block. And it should do that easily without a large or complicated key. So which steps can we take to make this block cipher thing implementable? So here you see like a sort of a big view of a block cipher. The message block goes in, the ciphertext block comes out, and the key configures the whole thing. And now there are two important simplification steps that make this whole thing implementable. And the first one is that instead of having one big circuit that evaluates the message or that encrypts the message, what we want to have is a simple circuit. But because a simple circuit alone is not good enough, we need to repeat it a number of times. So we want a simple function called the round function that we repeat r times. So it's the same thing repeated r times. And the individual rounds are then configured by the key. And to say in what way the key influences each round, we have a key schedule, which expands the key and gives a part of the key into every round. Now we still have to think that we still haven't solved the problem of how the key should influence each round. And now there is one construction here which almost all block ciphers share. And that is the following. This is what makes it the so-called key alternating construction. It says that we alternate between unkeyed rounds and key additions. So we first we have the circuit here, which is publicly known, independent of the key. We execute it, then we XOR the key to the output. Then we run again the round, XOR the key to the output, and so on, until the final round. And typically we also add it in the beginning and at the very end. So the point of this key alternating construction, so to alternate between key and no key, is on the one hand to avoid having any key-dependent circuitry. And this is also to some extent what Kerckhoffs's principle tells us to do. So it tells us to have an easily exchangeable key and to have a public algorithm. And having a public round function that is key independent is one way to do that. Not the only way, but a way. And so this key alternating construction is what many ciphers are based on. The remaining main questions are then, what should the round function look like? And maybe what should the key schedule look like? So the round function essentially has two jobs or two goals to achieve. Namely that each input and key bit, so message and key bit, should influence each output bit. So the effect of each bit of the input should be spread over the complete output. This is called diffusion. And second, this link between the input and the output bits should also be complicated, which is called confusion. So these are two very classic concepts proposed by Shannon, so already a long time ago. And they still give us some guidance about what the round function should be constructed like. And one very straightforward approach to this, or very classic approach to this, is the so-called substitution permutation network, or SPN, where the substitution part is responsible to achieve the confusion, so it's supposed to make things difficult. And substitution means it's a lookup table, so it substitutes the input by some output. But to make this feasible, we don't want the huge lookup tables for the whole thing, but we do it in small blocks. So we split our message again into smaller chunks, for example bytes, and let each of them go through a substitution table. And this substitution table should be strong and nonlinear, so it should not be a linear function, and it should have some properties that we will get back to in the cryptanalysis lecture. and it's small. And what the permutation then is, classically permutation meant you take all the bits that come out of each of these substitution tables and rewire them. So to lead, for example, if we have a substitution table of 8 bits, you take the 8 output bits and make sure that each of the output bits goes into a different substitution table in the next round. So to diffuse the effect from one of the inputs of the first table to all of them in the next table. If you found this confusing, no worries, I have a picture on the next slide. But what I want to say first is that while we call most modern ciphers SPNs as well, for example the AES, this bit diffusion or bit permutation isn't really happening there anymore. So what's usually happening instead is a linear mixing layer that is, for example, represented as a multiplication with a matrix. So any linear function can be described by a matrix multiplication, and this is what often happens here. So today, if we say SPN, substitution permutation, we actually usually mean substitution and linear mixing. But SP just sounds nice, and we're so used to saying it that we still use the word. So let's have a look at an example that follows very, very classically this SPN approach. And this is the so-called present cipher, which isn't actually that old, but the design principle it uses are very old. So this was proposed in 2007, this cipher. What it has is it has a 64-bit input, message input, where each of the message input bits is represented by an arrow here. It follows the key alternating construction, which means that after each round, some round key is XORed to the entire state, which is defined by the key schedule. And then we have the S and P steps. S means it goes into S boxes, so every 4 bits, all chunks of 4 bits go into one S box lookup table, which is simply a 4-bit to 4-bit lookup table. And afterwards, these 4 bits are taken by the bit permutation layer and dragged to different S boxes for the next round. Now the choice of this permutation is not random. You can see it looks quite regular, actually quite pretty. And this also has a purpose. And we see what this purpose is once we try to test the diffusion properties of this cipher. So this whole thing, here I show only the first 2.5 rounds. So this is 1 round, this is 1 round, and there is half a round, so 1 S-box layer at the end. But actually the full thing has 31 rounds. And this choice of 31 is actually pretty tight, so the best attacks are already very close to breaking this number of rounds. So currently I think the record is, I'm not sure, is it 27, 28, something like that. So the best dedicated attacks could attack up to this many repetitions, but not the full 31 currently. So let's have a look at what the diffusion looks like. So first, here's a representation of this lookup table. So this is simply a table which matches some value x and maps it to some output value s of x. So it can also be written as a function like s. Let's see now what happens if we, for example, flip 1 bit at the input of the cipher here. Or let's see which other bits this 1 bit influences. So first of all, it goes into the lookup table, and since this is supposed to be strong, it probably influences all 4 output bits of this table. Now these 4 output bits go to 4 different S boxes, and you see already that they are quite evenly spaced. Now each of these S boxes is sort of triggered or activated. So again, all of the 4 output bits here plus the 4 here and so on. So these 16 bits already depend on the initial key and plaintext bit. And if we repeat this one more round, then we see that actually each of the 4 bits of this S box goes to 4 different S boxes. The same thing happens here, but these are all disjoint. So they're all different, these positions. So for example, this one here takes again the 4 positions that we had before. And this one takes also every 4th S box, but it starts not at index 0, but at index 1. So overall, after just 2.5 rounds, we have already brought the diffusion up to the full state. So at this point here, the full state depends on this first input bit. But we still repeat many more rounds to make sure it influences them not just a bit, but very much. And in a way that is sufficiently complex that somebody who knows the plaintext and ciphertext cannot recover, for example, the key from that. Or also that somebody who knows the plaintext for one message cannot guess the ciphertext for a slightly modified message where we just flip a bit or so. Okay, so this is the concept of diffusion that we see here, and the confusion is going on inside the boxes and making sure that this dependency is not just there, but is actually complicated and statistically strong. Okay, now let's talk a bit about the cost of implementing such ciphers. So we've already seen now here the circuit of the encryption function. But the question is, what would the decryption function of this cipher look like? So here is a generalized representation of an SPN key alternating cipher. So of the round function, we see here some state that goes into the round function. Then the key is XORed, then it goes into S boxes. Then these are mixed in some way. We just call it P, and then that's the output. What would we have to do in order to decrypt this cipher? So we need to go backwards through all of these steps. If we want to implement that, then first, if we have this value here and know the key, we need to implement the inverse mixing layer. So in the previous example, that's quite easy because following the lines forward is as easy as following the lines backward. However, of course, I would need to, if I implement them in hardware or so, I would need to implement that separately so that I have a copy of the cipher that goes in this direction, and I have a copy of the cipher that goes in the other direction. For the S box, it's the same thing. In order to go back from here to here, I need to store the inverse lookup table. So from the output to the input. Finally, the key XOR, at least that's the same. So I use the same logic to invert the key, because if x plus k equals y, then y plus k also equals x, if plus is XOR. So here, in summary, to implement the decryption, we would need to implement the decryption of each individual step. So we essentially have to implement the whole cipher twice, forward and backward. And already in the very beginning of the public history of block ciphers, Horst Feistel came up with a very clever idea how to avoid that. So how to build a circuit where the same circuit can be used for encrypting and for decrypting. And this construction is called the Feistel cipher. So what this construction does is it takes the input block, but it divides it into two halves. And unlike SPN, where the entire thing goes into my SPN network, here I only feed one of the two halves into this function here, which has a similar structure as the other one. Then I take the result and XOR it to the other half. And finally, I swap the two halves. So in effect, the left output half here is identical to the previous right input half, whereas the right output half is identical to the left input half plus a function of the right-hand side. And then I iterate this construction. Now, the interesting thing is that the inverse circuit for this works exactly the same. So to invert this, I also take the one of the two halves, put it into the function, and XOR it to the other half. So I never need to implement the inverse of this one here. I always just feed one of the two halves into the function and XOR it to the other half, and then swap. That's it. So that saves me from implementing the decryption of these two things. However, the Feistel cipher also comes with some downsides, because you very often need more rounds of this than you would need of this. This is because half of the state is simply copied without being modified. And for this reason, we get a number of so-called somewhat generic attacks, because they do exploit the fact that it's a Feistel cipher, but they don't exploit the details of this function here. Okay, but this is still a great idea, but it was at one point more popular than it is now. So if you look at old designs, in particular, if you look at DES, for example, you see this, but more recently, it's a bit less popular. Okay, are there some other things we can say about the implementation cost? Well, if you think about having to implement this sort of thing in software, then you may already have wondered, how on earth am I supposed to implement these bit permutations that we saw in the case of present? This is really inconvenient because in hardware, this is super easy. You just have your wires and that's it. But in software, if you store your bits in bytes, for example, then in order to mix around the bits, you would have to mask out part of the byte, so to select only the particular bit and then shift it and then copy it somewhere else and then OR it together with all the other things that go into this new byte. So it's a big mess. It's very error prone to implement. It costs a lot. Not a great idea. This is one of the reasons why more recent functions don't use these bit permutation stuff so much anymore, except if they're really only targeted at basic implementations. Then there is also the fact that the S-box tables can be susceptible to timing attacks, because in the S-box tables you always make lookups, and if you think that some of these lookups are cached, that means that the following lookups of the same value will be faster than lookups of values you haven't seen yet. And from these patterns, you can recover some information about the processed data. So there is one main other implementation strategy that people use when it's more for software and less for hardware implementations, and that is the so-called ARX construction, where A is for addition, meaning integer addition modulo 2 to the 32. R is for rotation. So all of these are operations on words. So here inside the ciphers, you typically have the state, for example, written as 32-bit words, and then you can simply apply the addition instruction to them, or you can apply a rotation instruction, or you can apply an XOR. So these are all operations that are readily available on the CPU in just one instruction. And here you effectively get your properties, your confusion and diffusion from, so rotation and XOR contribute some diffusion, addition also a tiny bit, and addition is also the nonlinear operation here that contributes nonlinearity. So this is, for software-oriented ciphers, a good strategy. However, it has a very big downside, and that is it's a lot harder to analyze. So not harder to break, but harder to find out whether it's breakable. And SPN designs are a lot better analyzed in the sense of we have a better understanding of how secure they are. So we've now seen a bit about how to build a block cipher, but I've been speaking about all these other other primitives like tweakable block ciphers or compression functions, and I've also spoken about the need for different key sizes. And what generic compositions do is they try to address this by taking a block cipher. For example, in the early days of public crypto, they tried to build everything out of the block cipher DES and then do some wrapping and rewiring around it in order to get other primitives or bigger keys. So let's have a few examples. So the idea is, so far we've talked about dedicated construction, which means you build exactly what you need. But of course, once you've built it, you can only use it for that purpose. And if you want to use it for something else, like if you want to turn DES into a compression function, one thing you can do is a generic composition, building a wrapper around it. But of course, things can also go wrong when you do that. So let's have a look at first how to build block ciphers from block ciphers or from block ciphers without a key, which are called permutations. So the goal of this type of generic construction is to increase the key length and thus increase the security level of a cipher. Now, one very simple idea is if you have a block cipher like DES, but you're not happy with its key size, you could simply apply it not just once, but for example, 2 times or 3 times. This is called multiple encryption. So you build a new block cipher that internally simply iterates another block cipher. So this looks a bit like a round function, but it's really a fully fledged block cipher inside, but you try to build a better block cipher outside. And if you do this s times, you get a key of s times k bits as a new key. Instead of multiple cores, you can also extend the key size with a so-called whitening key, or fx construction, where f stands for the f function inside and x stands for the XOR of the key. So what you can do is, if you just want to increase your key size, you first XOR a new key, then do the original block cipher, and then XOR another key. And your total key size is then k bits plus 2 times n bits. You can also do this even if the thing inside doesn't even have a key yet. And this is the so-called even Mansur construction, which turns a permutation which doesn't have a key into a block cipher that does have a key, simply by XORing before and after the key, which can be the same or can be different. The thing is, these are unfortunately not as secure as you might guess at first. And to illustrate that, let's have a look at double encryption, which means I want to encrypt my data by first encrypting it under one key and next encrypting it under another key. We also saw an example of this in the exercises already. There it was a pretty simple example, and it was clear why double encryption wasn't so useful. But for general block ciphers, this adds quite a bit more. However, maybe not as much as you would hope. So this is the setup, and what I want to show now is a so-called meet-in-the-middle attack on this sort of double encryption that shows that the overall key recovery complexity is not 2 to the k1 plus k2, but less than that. And to perform this attack, I work as following. So it's a so-called meet-in-the-middle attack, meaning I work from outside to the inside. And I start by first querying or somehow obtaining one message ciphertext pair. What I can do now is I can try every possible value for k1, encrypt the message with it, so do this, and store the intermediate result here in some table, for example in a hash table. And I do the same thing for every possible key guess from here to here. So this part here, this costs 2 to the k tries. This one here also costs 2 to the k tries. So in total 2 times 2 to the k. And now for each candidate I have here, I look whether I can find the value that I get here already in the table that I computed for here. So I see if I can find a match. And if I have such a match, then I have one possible combination of a key k1 and k2 that would correctly translate m to my intermediate table value to the final ciphertext. So one candidate for the right key. Now I'm not done yet at this point because I will not just get one key candidate usually. Instead, so if I have 2 to the k options here and 2 to the k here, I have a total of 2 to the 2 times k combinations, and the probability that one of them is correct is 2 to the minus n. So if n and k are the same, the probability is 1 divided by 2 to the k also. So in total, the expected number of matches in that simple case where k and n are the same is 2 to the k. So this is how many candidate key combinations k1 and k2 I get. And of course, now I still need to test which of them is the correct one. So I would need to do a second query and compare whether my key combination matches with this second query. So what is the total complexity? I build these two tables and then I evaluate my 2 to the k candidates that I get. So in total, it's something like approximately a small multiple of 2 to the k tries, which is actually not a lot more than just breaking one of the block ciphers. It's definitely a lot less than a brute force attack on k1 and k2. And what I exploited here is essentially the birthday paradox, because I translated this key recovery problem into a collision problem. Okay, this is something you will also see again in the exercises. Now, since we're already talking about collisions, let's also talk a bit about building compression functions from block ciphers, since this is where we care about collisions. And one very well-known construction to do that is the so-called Davis-Meyer construction. And it works as follows. So what we have given is a block cipher E, and what we want to have is a compression function. And we can do this by using one of our two inputs, the state input, as an input to the cipher, and using the other input as a key. So far, so easy. So what that would mean is I could build a compression function by simply encrypting my state under the message. However, if I do that, I don't really get pre-image security, because I could then simply decrypt the value again using this key and get a suitable value S, which would be a problem, because this way, by being given a T and choosing some random M, I could find a suitable S, which would be a pre-image attack. So I want to avoid this. This means I still have to make it impossible to decrypt back from here. And one way to do this is to use this so-called feed forward here, meaning I not only put my input state into the block cipher message block, but I also XOR it afterwards at the end. And this way I can't get back from here, because to get back to the block cipher, I would already need to know the input of the block cipher, which I don't, because that's what I'm trying to recover. So I can't attack this. And there are a bunch of other ways you could put together the state and the message. You will explore a few of these combinations in the exercises and find out whether it's a secure combination or not. And there is one other issue here, and that is related to sizes. So if we do this with DES, for example, DES is a block cipher with 64-bit input blocks that would give us a compression function with only a 64-bit output. What security level does that correspond to? 32-bit security. That's not a lot. So doing this to DES is maybe not the best idea, but still most of the hash functions we have, in particular SHA-1, SHA-2, and so on, they all use this construction, but with a custom-made very large block cipher, which has a very large input and output state. Okay, so since I'm already talking about them, let's finally look at a few standardized ciphers. I've already mentioned DES, the data encryption standard, a few times. This is because it was the first publicly used block cipher. You can see its age in its parameters, so it has 64-bit blocks and 56-bit keys, both of which is very, very small for today's standards. Internally, so it was designed by IBM and later updated by the NSA, and is based on an original design by Horst Feistel, whose name you know already, because he invented this Feistel construction, and indeed DES follows this Feistel construction as well, in a total of 16 rounds. And it was quickly standardized by the National Institute of Standards and Technology. It's part of this 70s crypto that I also mentioned last week. And it survived quite a while before it was finally superseded by the advanced encryption standard AES in 2001. And quickly after that, DES was also withdrawn, simply because these key sizes were no longer really up to standards. They were actually already criticized at the time the design was published. And as the second factor, there were also some weaknesses discovered against the primitive of the cipher in the 90s, in the early 90s. So what does the F function of DES look like? Since it's an old cipher, it follows this SPN construction inside the F function at least. So it has S boxes and afterwards a bit permutation. What's noteworthy here is that the S boxes are not really S boxes as we usually know them. Usually the input and output size of the S box are the same, but DES is special here. It actually maps 6-bit inputs to 4-bit outputs. And it can do that because it's a Feistel function, and we said in a Feistel function, the function here doesn't actually have to be invertible. So in particular, we can also do this sort of compression step in between without being a real problem. So what actually goes on here is you first expand the message by duplicating some of the bits. So some of the bits go into 2 S boxes, and then you compress it back down again. So in other words, the neighboring bits influence which S box exactly is chosen, and this is then applied. So that's what DES looks like. There were the first theoretical attacks published on DES in the early 90s, as I said. So first, differential cryptanalysis, which we will also have a look at in 2 weeks, but probably not on DES, because this is really messy to look at. The attack that worked even stronger against DES, because it was not known by the designers at the time, is linear cryptanalysis. And unfortunately, due to the small parameter sizes, there were also some practical brute force attacks possible already in the 90s. Now, this is one of the reasons why we have these generic constructions I showed earlier, because people tried to fix DES in some way by increasing the key size, because they were already aware that the current sizes are not enough. So there were some temporary successors like DESX, which follows this FX construction, by XORing additional keys, or triple DES, which does DES, 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 either with different keys or with the same keys. And I've marked them with warning signs here because DESX is susceptible to the same attacks as DES, namely linear cryptanalysis. And triple DES is a bit better. You will evaluate the security of this construction a bit in the exercises, which I will upload later today. But it still has this very small block size, which is a problem in many protocols. And also, it's really inconvenient to implement in software. So if you want to use it for something like in your browser, so it's a really bad choice nowadays. Because nowadays we do have a successor, namely the AES, which I've already introduced in information security. So AES is actually a family of 3 block ciphers with 3 different key sizes. So 128, which is sort of the default, but to be secure for the future, they also added larger key sizes. The block size is always 128 bits. And this name originally, or the cipher originally had, before it was chosen, it had a different name. So it was named after its designer, Vincent Reimann and Johan Dahmen. So it was called Rheindal originally. And you still sometimes see people refer to the AES by this name. And it had this name because it was actually chosen as a part of a competition. So when NIST decided that DES should be replaced, they sent out a public competition. They asked photographers around the world to submit their designs, evaluated them for several years in the so-called AES competition, which already had the name before it was clear which cipher would actually get this name afterwards. And then in 2000, when the winner was selected, the name AES was transferred to this winner, which was Rheindal. As a side note, Vincent Reimann actually taught for a little while after around 2000 at TU Graz. So he was a professor here for several years. And he also used to teach the predecessor of this very course here for a couple of years. You can find the detailed spec of the AES in one of the NIST publications, in the Federal Information Processing Standard publication number 197, to be precise. Now, this cipher is also already more than 20 years old, but there are still no real known weaknesses under certain conditions. So it's extremely widely used and supported, so almost everything that you encrypt will probably be encrypted with the AES. And it also inspired many of the modern designs that we know. So what does it look like? As a reminder, in case you already know it, or as fresh information in case you don't. So it has 128-bit blocks and keys of the same size or larger. And this is also reflected in the names of the 3 cipher variants. So this 128-bit block is written as a matrix of 4 times 4 cells, which are actually exactly 1 byte each. So it's 16 bytes large, the state. And this is the way that a message is first written as a state, which is then updated by several round functions. And the key is also written as such a matrix state. And the state is then initialized to M, updated for a number of rounds, which is, in case of AES 128, for 10 rounds, where the last round is a bit different. And then the result after this many rounds is the final ciphertext block. So what are these round operations? So AES is often called an SPN, but it doesn't actually have a bit permutation inside. Instead, it has the following 4 operations. The first is a classical substitution layer, meaning a lookup table where we have a lookup table for 8 bits, and we use as the index one of the cells in the input before the round and write down the output of the lookup table. So this is sub bytes, or for short SB, where sub is for substitution. So this is the confusion layer, so to say. And then we have 2 operations that together form the linear mixing layer. The first of them is to distribute the cells of one column across the different columns of the matrix. This is called shift rows because each row is rotated by a certain number of byte positions. And then we have mixed columns, which is one of the promised matrix multiplications that we have. So we take the entire 4 bytes of one of the state columns, we do this for each column, and we multiply it with this 4 by 4 constant matrix and write down the result in the same position. Now, to explain how this multiplication actually works, you will need to wait a few more lectures because the multiplication here happens in a so-called finite field. So the 2 and the 3 here aren't actually the integers 2 and 3. They do have the same bit representation, but multiplying by them works differently. But we will explain that in 3 weeks' time, I think, how that works in detail. But for now, it's good enough to know it's a matrix multiplication, like the Hill cipher that we had in the exercises today. And finally, there is a round key addition, which is simply the XOR of the current round key according to the key alternating construction. So, what diffusion properties does it offer? So here is an illustration for the first 2 rounds of AES, which is a bit similar to what we saw for present. But I've only indicated not the individual bits, but just the byte. So any blue byte means it's influenced by the first blue byte here. So if we change 1 bit of this blue input message, the key addition doesn't do anything to that. After the substitution table, it influences all 8 bits of the same position. Shift rows shifts it around, which in this case does nothing. And then comes mixed columns, and mixed columns has the special property that if only one of the input cells in the column is different, then all of the output cells in the column will be different. We will explore this property in more detail in 2 weeks' time. So this means that after 1 round, the bit has already influenced 32 bits. And in the next round, we have a similar effect as before, so afterwards the entire column is influenced. This is now shifted into different columns, and now mixed columns blows up each of this 1 byte change to a 4 byte change. So here, after only 2 rounds, we already have this effect that each bit here influences each bit here. This is a property that's also called full diffusion. So it reaches full diffusion after 2 rounds. Whereas the present design needed 2.5 rounds for this. But both of them are very much optimized for achieving a fast diffusion. Finally, for the last few minutes, let's look at a few hash designs. I've already announced that these hash designs are all based on block ciphers. Both of these candidates here were designed in the mid-90s. So MD5 in 92 and SHA-1 in 95. Both standardized or used or recommended by NIST, or at least this one here in the secure hash standard, but this was also very widely used. However, there were already first practical and theoretical attacks on these pretty soon. So for MD5, it was first some attacks on the primitive that could not yet be translated into an attack on the full hash function. This took a few years, but then it works as well. And for SHA-1, the first theoretical attacks were published together because they were based on the same strategy as the collisions for MD5. And again, it took a long time until this could be translated first into practical collisions of the primitive, so the theoretical attack into a practical attack, but as of yet only on the primitive without actually being able to do something for the full hash. And finally, in 2017, this was extended to a collision of the full hash. And on the bottom right here, you see 2 examples of colliding PDF files. So the blue beige thing and the red beige thing are 2 PDF pages which both hash to the same SHA-1 value. So as an illustration that you can construct some actual meaningful collisions with this technique. What did they lead to, or which current successors of this do we have? Well, there's mainly SHA-2, which is a family of construction of compression functions using exactly the construction we saw before, with very large compression functions. The mode is one that you already know from InfoSec and that we will revisit in a few weeks. And this one was also standardized by NSA, but so far no real weakness has been published. So in particular, SHA-2 is still fine to use. It was not superseded by SHA-3. You can see here a short illustration. It's just the Davis-Meyer construction that we already mentioned. And you see that the message is used as the key, expanded in a key schedule, and this key schedule influences each round. You can't see much of the rounds because there are 64 of them, so each of them is very small. And at the end, the input is again XOR to the output. And SHA-512 is the same thing, just in bigger. And for the round function, this is something like a variant of the Feistel construction. So you see you have multiple branches here, which are shifted to different positions, and they all go into some update functions which are added to another of these branches. So it's like a generalized Feistel construction. And this actually happens in both halves. And inside you have some linear functions called sigma, which contain XORs and rotations, and you have some bitwise nonlinear functions. So this whole thing is a bit of a mix of different designs inside here. So if you look just at this part here, it looks like an ARX design because you have R and X inside here and A here. However, it does also mix in these bitwise update functions. So it's like a generalized ARX scheme and mainly intended for software. But it was accompanied by another alternative design, namely SHA-3, or originally called Ketchak. It again came out of a competition, which follows a completely different approach. So it also has a very large intermediate state, but it uses a very different mode. And the internal primitive is not a compression function, but a permutation. It's quite a bit newer than all the other designs we saw so far. You will notice that one of the designers is one of the people who also designed the AES. So he was successful in 2 of these competitions. And SHA-3 was selected in 2012 and standardized 5 years ago by now. However, it hasn't yet made it into too many actual applications. So, for example, it's not yet part of TLS, for example. But I'm sure it will end up there in the future because there are quite a lot of advantages compared to SHA-2. And it also has a larger security margin. Security margin meaning the remaining number of rounds that are still not attackable, essentially. So here's a short peek at what the internal primitive looks like. We have, as I said, a state of 1,600 bits, so really, really large. And this is also written as a matrix of vectors. So here it's not 4 by 4 like in AES, but 5 by 5. And each of these things in here is not just 1 byte, but it's a full-blown 64-bit word. So this state is really a lot bigger than the AES. And its entries can then also be labeled along these 3 dimensions. So x-coordinate says the column, y-coordinate says the row, and z-coordinate says the position within the 64-bit word, where 0 is the least significant bit and 63 is the most significant bit of this word. And the operations that it uses are thankfully, from a mathematical perspective, quite a bit easier than in the AES. So there are no strange matrix multiplications or so over some finite field, but it simply uses XORs, ANDs, and rotations. And this choice of operations is both hardware and software friendly, because all of the operations, or most of them, are register oriented. So you can always take the full 64-bit words and, for example, XOR them or AND them together, or rotate them within the 64 bits. But at the same time, it's also relatively easy to do in hardware. And the bad news is that while the individual operations are a bit easier, the full thing is a bit harder to understand. So for one thing, you have 5 intermediate operations, and they're conveniently labeled by Greek letters. So we have the theta step, the rho step, the pi step, the chi step, and the iota step. Very easy to remember. So what do these steps look like? Let's first look at the linear steps. So we are now having several linear steps that try to diffuse along the individual axis of the state. So we have the theta function, which works as follows. So it updates each of the 25 words by adding the sum of all the words in the column to the left of it, plus the sum of all the columns of all the words in the column to the right to it, but shifted by 1. So in total, you take these 10 64-bit words, you shift half of them by 1 position, you XOR all of that together, and you XOR it on top of every cell in this middle column here. So this way, any bit change, for example, in a bit influences both its neighboring columns. So this is a sort of diffusion between the different columns. And then here we have a diffusion along the z-axis, so between the least and most significant bit. And this happens by taking each of the 64-bit words and rotating it, but by different amounts. So you here in this picture, you see by how many bit positions the particular word in this position is rotated. So the top left one is rotated by 25, and the next one by 39, and so on. So these are not shifted, so you don't lose the overflowing bits, but rotated. So you shift and then take the overflowing part and copy it to the other half. You know how rotation works. Okay, so this is along the z-axis. Now we still need to shuffle a bit around between the rows and columns in general. So here now we have a very messy alternative to the shift row step of AES. Here a lot more shifting and exchanging goes on. So here you always see the word in the red position moves to this other position indicated here. And since there are a total of 25 different movements, I couldn't fit them all into one picture, but they essentially all are happening at the same time. But you see, it's a pretty messy picture. There are some regularities, but it's impossible to remember what exactly goes on. So all of these are linear operations. What we are still missing is something nonlinear. And this is where the S-box comes in the key step. So this is now a 5-bit S-box, which is a bit unusual because most ciphers use either 8-bit or 4-bit S-boxes, but it actually has quite some advantages. And so this S-box, and this is now very different from the AES, this S-box is not applied within one of the cells, but across the cells to make it more register-oriented. So the S-box works on each row here, takes all the 64-bit words in this row, and then applies the following register-wise operations to it. So you can see here the circuit. This includes some ands. These are the little triangles here. It includes some knots, some ands. These are the C dots here, and some XORs. So what effectively happens here, it takes any two neighboring registers, toggles all the bits in one of them, ANDs them together, takes the result and XORs it to another neighboring step. So it's always take two registers, flip one, AND them, and XOR them to the next neighbor. So this is usually not implemented as a lookup table, even though you could describe it bitwise as a lookup table, but it's simply implemented as register instructions. Okay, and finally there is some round constant that is added to make sure that all the rounds are different, because if they aren't, there are particular types of attacks that would be possible. Okay, I still have 1 minute left. That does not satisfy me exactly, so we will need to skip this Mentimeter question, but we will jump right to the conclusion and we'll be almost on time. So what did I try to convince you of today? I tried to convince you that primitives are the foundation of security in symmetric cryptography. So they take simple non-secure operations and iterate them in a way that they become something secure. And how secure should be at least as secure or as secure as the interface promises. So there should, for example, if you have a 128-bit key, you shouldn't be able to find a faster attack than guessing the key. Now what's important is the security of these primitives cannot be proven. So you can't do a security proof over the primitive. It can only be analyzed by trying to break it. And we'll see how to do that in the following lectures. You can only prove something if you do one of these generic constructions where you turn one primitive into another primitive. Now for widely used primitives, we've seen some classic and outdated ones, but also some who are currently still very much in use. And in particular, if you look at TLS, so at HTTPS, in the newest version, you will see that only very few primitives are supported. So first there's AES with 2 key sizes. Then there's a stream cipher called ChaCha20. We'll have a peek at that next week. And then we have the SHA-2 compression functions. So maybe I didn't explain that clearly at the time I explained SHA-2, but SHA-2 has 2 main family members, which are named after their hash output sizes. And these are called SHA-256 and SHA-512. And all of these ciphers here are expected by the research community to provide security for quite a time to come. And in particular, they also retain quite good security levels in a post-quantum world. So they will not completely break if we have so strong quantum computers. They will just get a slightly lower security level. Okay, that's most of what I wanted to tell you. I'm definitely open for questions now, as long as you have them. You can either ask questions in the chat here, or you can also stay on your Mentimeter thing and ask the questions there. So I will now show all the questions that are popping up from there, and also have the chat in the corner of my eye. So if there's anything you didn't understand or that you're curious about, just give it a go here. And I'll wait for another 5 minutes or so, and if nothing pops up, then I'm a bit dissatisfied, but I will still see you next week. No questions coming up and people already leaving. Then maybe one question from me to you. Would you usually prefer to have another break during the lecture part, or are you fine to just have one long thing in it? Any preferences? Break would be nice, or it's fine the way it is. Okay, so I can essentially choose what I prefer. What about multiple encryption with more than 2 blocks? Finally, thank you for asking a question. So when you do more repetitions in multiple encryption, you do gain some security. So for example, a triple encryption is significantly more secure than individual encryption, as you will also see in the exercises. So in particular, triple DES is definitely stronger than single DES, whereas 2 DES would not be stronger. So you do gain something by more repetitions, but you always don't gain as much as you would like. So one rule of thumb is that you gain something like 1 or 2 repetitions less than you would hope if you look at small multiples of encryption that you can do. So it does make sense, but it's not as good as you'd expect, and it often makes more sense to just design a new cipher if it's at all possible to do. Okay, it appears like not too many more questions are coming. I will close the YouTube stream for now. I will stay on Teams a tiny bit longer if you still come up with something.